Hello everyone, in this video I will talk about concrete mix design. Concrete mix design is to determine proportions of mixed ingredients, including cement, water, coarse aggregates, fine aggregates, and the use of admixtures. The goal is to have acceptable workability of fresh mix and have desired durability, strength, and appearance of hardened concrete, and also be economical. Strength is the most controlling design factor. We often use FC prime to denote concrete strength. It refers to the average compressive strength of 3 different tests. Each test is the average result of 2 6-inch by 12-inch concrete cylinders tested in compression after curing for 28 days. So in order to achieve these 3 characteristics, the material engineers must determine the proportion of cement, water, fine and coarse aggregates, and whether or not we want to use admixtures. The basic steps for concrete mix design include strength requirements, determine water to cement ratio, estimate coarse aggregate mass, and determine whether or not we want to use air entrainment. And also evaluate workability of plastic concrete and estimate water content of the mix, and determine cement content requirements, evaluate whether or not we want to use admixtures, and estimate fine aggregate mass, and determine moisture corrections. In the end, we make and test trial mixes. Let's first talk about the first step, strength requirements. Structural design engineer will specify a strength of concrete to be used in the structures. We call it FC prime, and when they specify this value, they do not consider the variability of concrete materials. So if the material engineer provides a material with an average strength exactly equal to the strength specified by the designer, then half of the concrete will be weaker than the specified strength. Obviously, this is undesirable. So in order to compensate for the variance in concrete strength, the material engineer will design the concrete to have an average strength greater than the strength specified by the designer. So only a small portion of the concrete will have a strength less than the specified strength. Actually, American Concrete Institute, ACI, states that there should be less than 10% chance that the strength of a concrete is less than the specified strength. Assuming that the concrete strength will follow a normal distribution, so we will have this curve as shown in this picture. And here we use mu to denote the mean and use sigma to denote standard deviation. So they are calculated based on these 2 formulas. And the area under this curve between any 2 values represents the probability of occurrence of an event. For example, the probability of occurrence of an event between this value, which is the mean minus standard deviation, to this value, mean plus standard deviation, will be 68.3%. And between this value, mean minus 2 times standard deviation to mean plus 2 times standard deviation will be approximately 95.5%. And the probability between the mean minus 3 times standard deviation to mean plus 3 times standard deviation will be 99.7%. So actually, this is almost 100%. So you can see if the material engineer make the specimens which have a average strength exactly equal to the specified value, then 1/2 of the specimens will be weaker than the specified strength. And therefore, we want to make the required concrete strength higher than the specified compressive strength. For example, this is the required average compressive strength, and the specified compressive strength is somewhere here. Then, since the sample will follow the normal distribution, then we will have about 90% of the samples having a higher compressive strength than the specified value. So this is exactly what we are doing. So actually we use this formula FCR prime equal to FC prime plus 1.34S. Use this formula to calculate the required average strength for mixed design. So this is the actual average strength when we make the material. And this FC prime is the concrete strength specified by the designer. And this is higher, so the actual average strength is higher than this value by 1.34 times standard deviation. So we're adding this value to FC prime, and then about 90% of the concrete will be stronger than the specified strength. And S, which is the standard deviation, should be based on more than 30 tests or extensive history of the plan. If S is calculated based on fewer than 30 samples, then the standard deviation is underestimated. Then we use this table to find the modification factor F. So for example, the standard deviation S is calculated based on 15 tests, then S should be multiplied by the modification factor 1.16. If it's calculated based on 20 tests, then S should be multiplied by 1.08, and so on. And if you have a value which is not shown in this table, then you need to use linear interpolation to calculate the intermediate number, to calculate the modification factor. For example, if you have a standard deviation calculated based on 17 tests, it's not shown in this table, but it's somewhere between 15 and 20, so then you can use linear interpolation to calculate the modification factor. So after S is multiplied by the modification factor, then you compare S with 500 psi. If it's smaller than 500 psi, we use this formula to calculate the required average compressive strength. If it's larger than 500 psi, we use this formula to calculate the required average compressive strength. If fewer than 15 tests are available, or S is completely unknown, then instead of using these two formulas, we will be using the formula shown in this table. So if S is completely unknown or calculated based on fewer than 15 tests, then we will compare the value of the specified compressive strength with 21. If it's less than 21 MPa, then we use this formula to calculate the required average compressive strength. If it's somewhere between 21 and 35, then we will use this formula to calculate the required average compressive strength. And also, if it's larger than 35, we use this formula instead. So these estimates are very conservative and will not be used for large projects because the concrete will be over-designed, so it's not economical. So let's see an example about how to calculate the required average compressive strength. So the design engineer specifies a value for concrete strength, which is 31 MPa, and it asks us to determine the required average compressive strength for 4 different cases. So the first one is a new plant for which S is completely unknown, and second, a plant for which S equals to 3.6 MPa based on 17 test results. And third case, a plant with extensive history of producing concrete with S equal to 2.4 MPa. And the last case, a plant with extensive history of producing concrete with S equal to 3.8 MPa. Okay, so let's see the first case. Since it's a new plant for which S is completely unknown, then we need to use the formula in this table, right? So we need to decide which formula to use. So we need to compare the specified compressive strength Fc prime with 21 and 35. So the specified value is 31 MPa. So it's between 21 and 35. So we need to use this formula. So FCR prime equal to FC prime plus 8.5, which is equal to 31.0 plus 8.5 equal to 39.5 MPa. Okay. Second, we have a standard deviation based on 17 test results. So we need to find the modification factor by using linear interpolation. So we know that 15 corresponds to 1.16 and 20 corresponds to 1.08. So we want to know 17 corresponds to which value. So we have 20 minus 15 over 1.16 minus 1.08 equal to, assume this value is equal to x, then 17 minus 15 will be 1.16 minus x. So 1.16 minus x equal to 1.16 minus 1.08 times 17 minus 15, and then divided by 20 minus 15. Okay, so then we can calculate x, which will be equal to 1.13. So this is the modification factor, and S will be equal to the value of S 3.6 times the modification factor 1.13, which is equal to 4.1 MPa. Okay, so after we get this 4.1 MPa, which is about 590 psi, then we want to determine the required average strength. So 590 psi is larger than 500 psi, so we need to use this formula. So FCR prime will be equal to FCR prime equal to FC prime plus 2.33s minus 5 plus 2.33s minus 5 psi. So this will be equal to if you calculate, it's 5390 psi. Okay, so the next two questions. Okay, problem C. We have a plant with extensive history of producing concrete with S equal to 2.4 MPa. So 2.4 MPa is approximately 350 psi. So 350 psi is less than 5 psi. So we need to use this formula. So FC prime CR prime equal to FC prime plus 1.34 times S, and S is provided, so you can calculate. So this should be equal to 4970 psi. The last question. So we have a plant with extensive history of producing concrete with S equal to 3.8 MPa. So 3.8 MPa is equal to 550 psi. So then it's larger than 500 psi. So we need to use this formula here. So FCR prime equal to FC prime plus 2.33s minus 500. So this will be equal to, if you calculate it, it's 50 to 80 psi.